Okay, that's
Yeah.
great. Okay, very good. Yeah.
Okay.
Hi, everyone. I'm happy to introduce Professor Lei Zhang from the University of Florida, United States. Professor Zhang got his PhD from Rutgers University in 2001 under the supervision of the Professor Yan and me. After that, he was employed at Texas A&M, University of Alabama, Birmingham, and now University of Florida. And he's going to talk about the Blowup solutions and the vanishing estimate for the singular Liouville equations. Please welcome.
Okay, thank you for the introduction. It's my great pleasure and honor to speak in this seminar. I have never been talking to people from different continents. This is my first time, so it's such a pleasure. I also realized that some of them have heard this talk before, so I apologize for the repetition. Okay, so I'll be talking about my joint works with Professor Juncheng Wei, as well as my student, Lina Wu. And the equation is very short, only 3 terms. It's a 2D equation. As you can see that it's defined locally. Laplacian b plus h of x is a positive smooth function, an exponential nonlinear term. And then there are Dirac mass placed on the right-hand side at the origin in particular. And then it is defined locally on B1. And then alpha tells you the strength of this singularity, and then it has to be bigger than -1. And since 1/2 pi log x is a fundamental solution, you can just multiply 4 pi alpha on both sides, and then subtract 2 alpha log x to rewrite this equation in the equivalent form, which is Laplacian u plus x to the 2 alpha h of x e to the ux equal to 0. So for this locally defined equation, looks very simple. Then I'll be mainly talking about what happens when alpha is equal to a positive integer, which is the most interesting case, and that finds most applications. Okay, so this equation is very well known to the PD community, and partly because it is related to the famous Nuremberg problem. Nuremberg asks which function k on S2 can be considered, can be realized as a Gauss curvature, okay, conformal to the standard metric. So if you rewrite this equation, if you interpret this question into a PD equation, is to find which k, and then for what u for a k, this equation has a solution. And then you can, of course, this equation has no singularity, but there's a corresponding problem which says in the neighborhood of 1 point, if the metric has a singularity, can be written in this way, e to the smooth function z to the 2 alpha. And then in this case, we say at this point, it has a conical singularity of order alpha. And then the corresponding PDE to study is Laplacian u plus kx, x to the 2 alpha e to the u equal to 0. And then again, I want to mention one more time, the most interesting applications correspond to alpha equal to a positive integer. Okay, and then now moving. Okay, and then first, before we talk about the results about local equation, I'd like to mention a very well-known classification theorem by Wenxiong Chen and Congming Li in the year 94. If you have a solution, Laplacian u e to the u defined globally with finite energy, and then all the solutions can be written in a very specific form. And then if you look at this form, you will see that there's a radially symmetric, it is symmetric around x naught. You place any x naught, you place any lambda as a real number, then that's a solution. So in other words, the solution can be described by 3 parameters, lambda, and the 2 components of x naught. Okay, and then all the solutions have only one energy. The total integration of e to the u is equal to 8 pi. And then this one has a scaling property. So if you rescale the function, then you still have a new solution. Here, I give a picture about one solution, what the solution looks like. Since the total integration is always equal to 8 pi, you can imagine that if the height, which is represented by lambda, is very, very high, and then the whole picture we call standard bubble is very skinny, very thin, and which means the energy is very much concentrated near the neighborhood, around the neighborhood of the center of symmetry. Here, I'd like to mention to you that this theorem was motivated by a very even more well-known theorem by Cavalli-Gitas-Bragg for the Yamabe type equations. I guess everybody in the mathematical in the PD community knows that result, which serves as a foundation for Blowup analysis for Yamabe type equations. Okay, so this is the story about the global solution. And then here, the first result I mentioned about local equation. As you can see here, I'm talking about the story when there's no singularity at all. So when alpha is just equal to 0. Here, I'd like to mention a result by Yan Li, which is about this simple looking equation, Laplacian UK plus h e to the UK, defined globally. And then we just post some, we just mentioned some very ordinary assumptions. Suppose the sequence of solutions indeed is blowing up, say at the origin, and then apart from this condition says apart from the origin, there's no blow up point. So in other words, the only blow up point in B1 is just at the origin, and then there's a uniform bound on the energy. And this condition, the last one, the number 3. If I've never seen this before, is just the oscillation on the boundary, UK of x minus UK of y less than equal to c. Less than equal to c simply says on the boundary there's no wild oscillation. Oscillations, we call this oscillation, boundary oscillation finiteness assumption. So later I'll say a few words about this assumption. And then Yan's result is that for this locally defined solution, and then this one can be approximated by a sequence of global solution with the same height to the order of big O1, which means this is called uniform estimates. Just now in the previous slide, I said if for the global solution, if the height is very high, then the solution has a very long neck. So based on this, probably you feel that this estimate is not that trivial. Actually, the first proof is very challenging and very challenging for new students. And then later, there's a simplified proof. But this one tells you that for locally defined solution, blow-up solutions can be uniformly approximated by global solutions of the same height. And then, so what is the use of this? Usually people talk about the local solution in order to apply to globally defined solutions. So what is the corresponding equation defined globally on the manifold? Suppose the manifold has volume equal to 1. Manifold means the surface because we always talk about the second or 2D equations. And then this is the right setup. We call this mean field equation. The reason we have a -1 over here is because on the surface, when you integrate on the left-hand side, you have 0. So you have to have this term integral of this term equal to 0. Otherwise, it makes no sense. So for mean field equation, so Yan's estimate implies a few things. It implies that around each blow-up point, there's only one bubble profile, which means if you look at the weak convergence, it is converging to 8 pi delta p. Suppose p is a blow-up point. And then a second consequence is that suppose you have multiple blow-up points, then the height around each blow-up point, the heights of the bubbles are roughly the same. So the only difference between the heights, any two heights, is just big O1. And then the total integration of h e to the UK is concentrated near just around a few blow-up points. Okay. So these are the advantages of this estimate. But this estimate did not tell you the locations of blowup points, and also for some certain applications. And then it is not enough. The estimate is not accurate enough. Okay. So the next slide, I want to make a remark about this. Just now I said, in order to obtain Yan-Yan's result, you need to assume that the oscillation on the boundary has to be uniformly bounded. So if you take any x and y on the boundary, then you don't have wild oscillations. In fact, if you remove this assumption, boundary oscillation finiteness assumption, then Xiu Chen has a result many years ago. He says, oh, he can construct. Look, he doesn't even bother to have a different h. H can be taken identically equal to 1. And then he can construct for any given positive integer, for example, 5,000, then he can construct 5,000 bubbling disks all tending to 1 point. And as a result, e to the UK weakly converges to 8 pi m delta 0. Just imagine how bad the picture is. So for any m, he has m bubbling disks. They're all extremely tiny. And then inside each bubbling disk, there's a profile of a global solution. Okay, they're all tending to the same point. So this assumption, but I have to say that the applications, so this one is usually satisfied. So it's not a major it's just an assumption for convenience when we talk about local solutions. So usually it's not a problem. Okay, so this is, I'm still talking about the case when alpha is equal to 0, when there's no singularity. And then what I want to say next is that usually, since the oscillation on the boundary is finite, if you define a harmonic function in B1, and then on the boundary you define UK of x minus the average of the value on the boundary. Since the boundary oscillation is finite, so phi k of x is uniformly bounded down the boundary. And then we know that for harmonic functions, so it has mean value property. So this function, all the sequence of functions are tending to equal to 0 at 0, and all the derivatives are bounded inside, say, B1/2. Okay. And then with this set of harmonic functions defined, we can give a much better estimate than Yan-Yan's estimate for this simplest case. So I take UK of 0 to be a scaling factor. And then as you can see, the theorem coming from quite a few people, Junquan Chen, Chang Shoulin, myself, and my student Glock. This is not the sharpest estimate, but I can, since it is very closely related to the main theorem I'm going to mention later, I just want to point to you. So the expansion, this is like a tail expansion of Blowup solutions. The first term is a sequence of global solutions with a slight translation. Don't worry about it at this moment. And then Yan-Yan's estimate basically says, besides this term is big O1, but this big O1 can be a lot more specific. What is the second term? A set of harmonic functions with bounded oscillation on the boundary. And then the next term, I want you to pay attention to this term because this term has a Laplacian log h over here. And then there's a scaling factor. And then even this term is quite important, log term. Log term squared, even this will be closely related to what I want to mention about the main theorem for today's talk. And then there's an error term, which is scaling factor multiply log. And then in addition to much more precise expansion, we also have information about the location of the Blowup point. The Blowup point has to be the critical point of the coefficient function together with the harmonic function that eliminates the oscillation of UK on the boundary. And then the oscillation, so the Blowup point has to be a critical point and vanish at a certain order. So yes, for many people, You may, if you have never seen this before, you may wonder that why do you need to have such a precise expansion? And why do you need to know the location of a blow-up point? And then what's the purpose of doing such a refined estimate? Let me show you one theorem by Junquan Chen and Chang Shoulin in 2003. So they are talking about this equation, the mean field equation defined on the manifold. Look at this. They said the statement says, if rho is not a multiple of 8 pi, and then look, the genus of the manifold is greater than 0, then the equation has a solution. Genus is the number of handles of a manifold. If this is the first time you have seen such a theorem, I wonder if you're impressed by the beauty, because this one is talk about the topological information of the manifold. We know that for a donut, unless you rip it off, you stretch it, then the topological information is not even changed. And however, in order to prove such an existence result, you need very delicate local analysis. So the theorem links a very delicate local analysis with the topological information of the manifold. So that's why it is very impressive. Okay, I can say a few more words about how they did that. Roughly speaking, there's an a priori estimate. So this is guaranteed by the classification theorem and a certain block analysis. So roughly speaking, that when rho is between any two multiples of 8 pi's, and then if you place solution in certain space, there's a priori estimates. And then you apply Laplace G, which is a compact operator on both sides, and you rewrite the equation, rewrite the solution as a solution of I minus T rho. Okay, so it's identity minus compact operator. And once you have a priori estimates, you can choose R large enough, and then all the solutions can be considered as a pre-image of 0. Therefore, the degree, which only depends on, which is homotopy invariant, only depends on the topology of the manifold. And then the existence theorem comes from the calculating of the Larry-Shelder degree, which is very impressive. Only depends on the Euler characteristic constant of the manifold. So they prove this, and then based on this, they derive when d rho, which roughly says is a certain way of calculating the number of solutions. If it's not equal to 0, then you know the existence of a solution. Just mention one more word about this. The theorem fails, the degree counting program fails if rho is actually equal to 8 pi. I want to give you a sense of what level of research this one is being carried out. When rho is equal to 8 pi, Chang Shoulin and Qinghong Wang, they talk about this case in the paper when the manifold is just a flat torus. And then, of course, the paper is very involved. So they covered this in their paper, and that paper made it to annals. Okay, so this is the story about when there's no singularity at all. And then next, I want to talk about what happens when the singularity is very easy. So in other words, if the singularity is not an integer, so the singularity has to be bigger than -1. And then before that, let me follow the same storyline. I'll first talk about what happens to global solutions. So this is a well-known paper by Prajapat and Tarantello. They said for globally defined solutions. So again, the procedure is before I talk about the local solution, I want to talk about the global solution, a classification result. So if you have a globally defined solution with a finite energy, and then it is important to say that alpha is not an integer. And then all the solutions are radial solutions. And then again, they only have one energy. and then there's a scaling property. So all the solutions, again, they look like very when lambda is very high, very big, and then the bubble looks very thin. Okay, very concentrated. Okay, roughly speaking. Okay, and then corresponding to Yan's uniform estimates, Bartolucci, Junquan Chen, Chang Shoulin, and Tarantino prove a corresponding result. So they said they prove that when you have a locally defined blow-up solutions, okay, only locally defined, and then with the usual assumptions, we have just one blow-up point, and then bounded oscillation, and then they proved this one is very similar to Yan's result. You have a blow-up solutions, then you have a sequence of global solutions, and then the only difference between them is big O one. Okay, and then this result was improved by myself quite a few years ago, which says this. Assumption is still not a positive integer. This is very important. So you have a sequence of blob solutions, then you have a sequence of global solutions as the first term, and then what is the second term? The second term is the set of harmonic functions that I said before eliminates the boundary oscillation, and then the next term can also be identified, which is very specific about the gradient age, about the first derivative of the coefficient function. And then the next term can also be identified, which is involved with the Laplacian of the coefficient function and the first derivative. And then there's a logarithmic log term, and then a scaling factor, and so with a sharp estimates. And then the coefficients over here, lambda 1, lambda 2 can be determined very specifically. And as you can imagine, that corresponding to this result, there's also a degree counting program done by Chen and Lin. Okay, so all these are introductions of the main theorem I'm going to present right now. So what I really want to talk about is when the singular source is a multiple, is just a positive integer. This one has the most significant applications and most challenging most challenging situations in analysis. So as before, I first talk about the global solutions. And then for the global solutions, suppose you have a finite energy, and then I'm using Z to represent a point on the complex plane, because in R2, I identified it with a complex plane. And so this is a classification theorem by Project Head and Tarantino. They also have a classification of all the global solutions in this case. As you can see, let me briefly explain this expression. This expression has a picture like this. So this one says, if you put in any lambda, any real number lambda, and you put in any complex number psi, and then you still you have a solution. And then again, this is a family of solutions described by 3 parameters, lambda and also psi. But obviously, all the local maximums are determined by the psi. So there are roots, n+1 roots of psi. And then I give you one picture over here, which corresponds to n equal to 3. So I take psi to be, say, 1, take 1. And then as you can see from the picture that there are exactly 4 local maximums of the solution. And so obviously there's no radial symmetry, obviously. But what do you say? There is some sort of symmetry, which means when you look at the locations of the local maximums, they are evenly distributed around the unit circle in some sense, around a certain circle. Okay, so this is very, so the picture obviously is a lot more challenging than previous cases. And then, but it's important in application. Okay. Then let me move on. So a natural question is, suppose you have a sequence of solutions defined locally, and then you place the usual assumptions that 0 is the only block point, n is a positive integer, UK has bounded oscillation on the boundary. Then is it possible to obtain corresponding results? It turned out that it is a lot harder than previous cases. The research of this one was dormant for many years, and then it was proved by Theorem and Chang Lin. They had a breakthrough. They proved this. Let me describe the situation. They said that so they have this inequality. What is this inequality? This inequality says when the Blowup solutions violates the spherical Harnack inequality, the spherical Harnack inequality simply says you take the origin and then you draw a circle. So which means if the 2 points on the boundary of the same radius, they are not within O1, the difference between of them. So the difference between them is not O1 anymore. And then if this happens, if the difference between them is, if they satisfy spherical Harnack, that's much easier. Okay, so when the spherical Harnack inequality is violated, so even for locally defined solution, Chang Lin, Ting Guoli proved that UK has exactly n+1 local maximum points, evenly distributed around 0. In other words, this theorem says that even for the locally defined solution, because we know that for the global solution, this is the phenomenon described by the global solution. And then they said for local solutions, they also exemplify this kind of behavior. And then they have other estimates as well. And then this one was also proved by Bartolucci and Tarantello independently in a different paper. Okay. But it becomes extremely hard to obtain further information and pointwise information, very satisfactory pointwise information. So there are certain questions that can be addressed, which is it possible to approximate public solutions by global solutions? Is it possible? So are there vanishing theorems, especially the vanishing estimates of first derivatives of second derivatives? Okay. So the main theorem I want to mention in the joint work with Juncheng Wei is that that UK be non-simple Blowup solutions. Non-simple simply means when the spherical Harnack inequality is violated under the usual assumptions, then along subsequence. So the conclusion is not only do the first derivatives have to tend to 0, and then but also the Laplacian of the coefficient functions also tend to 0. What's the so in other words, if I use a different perspective to talk about this result, for example, it says suppose the coefficient functions do not satisfy this. For example, Laplacian is not tending to 0. Then all the Blowup solutions, they must satisfy spherical Harnack inequality. And in that case, the approximation can be so much easier, okay, in some sense. Okay, and then the non-simple assumption cannot be removed because non-simple means the spherical Harnack has to be violated in order to have the vanishing of the coefficients, not only the first derivatives, but also the Laplacian of the second order derivative. My student Lina Wu constructed a sequence of Blowup solutions that satisfy the spherical Harnack inequality, but these Blowup solutions do have non-vanishing coefficients. So this assumption of non-simple Blowup cannot be removed. Before I talk about further information about the idea of the proof, I'd like to mention to you that in comparison of these two statements, the first one is the gradient estimate of the first derivative vanishing estimate. The second one is Laplacian. The second one is a lot more important because it doesn't have the phi k in application. I'll mention many many situations that the theorem can be applied, but the second part is a lot more significant than the first part. Okay. Okay. The whole proof of the vanishing theorems is quite long and involved. That has to be explained in different stages. I was told to speak for 45 minutes, which is obviously challenging for me, but at least I can say a few key points before I. So as I said, for Blowup solutions, when the spherical Harnack inequality is violated, then there are exactly n+1 local maximums of the Blowup solutions. Their position is simply centered around a certain point, evenly distributed. Okay, and then the first thing is I take any one of them. I call it delta k. The distance to the origin is the delta k. And then I rescale the Blowup solutions according to the distance. So because the equation is more or less scaling invariant. And then after scaling, so mu k is the height of each of the bubbles. Of course, the height around each one of them is slightly different, but I just take any one of them. I call it mu k. Mu k is tending to infinity. Delta k is tending to 0. So this is the picture for n equal to 3. As you can see, there are 4 local maximums. And then after scaling, then there's the height of each of the local maximum is, one of them is mu k, and then the distance to the origin is scaled from delta k to 1, okay, roughly speaking. Okay. And then since the whole proof is very technical, I'd like to mention a few trivial observations before I get into more of the main ideas. So the first point I want to mention is that even though the picture looks very complicated because there are so many local maximums, the first point I want to mention is that the study of Blowup solutions looks like that of a single Liouville equation near each local maximum point. So near each of the local n+1 local maximums, so with the tools we use, that will be the study for the single Liouville equation with no singular point. That part has been very well understood. The second point I want to mention that the relations between these local maximums plays a crucial role. So in other words, we're not doing the local analysis around each Blowup point, around each of the n+1 Blowup points. Their mutual relation locations plays a very crucial role in the vanishing estimates. Then the third one I want to mention is that when we do the Blowup analysis around each of the n+1 points, so this one looks quite funny. It says, outside these n+1 points, the behavior of the function looks almost like a harmonic function. The reason I want to mention this because I'll be using a lot of Fourier analysis as well as Harnack inequality. So to pass the information around to each of the n+1 local maximums. And then another trivial observation is that when you look at the global solutions, then so I'm giving you global solutions, and then if you put one, then if you put one over here, and then all the local maximums will be exactly the n+1 roots of 1. And then if you just have a slight perturbation of 1 and you add a tiny little bit, then the n+1 local maximums will be just n+1 roots of this number. So if you perturb a little bit, then you also perturb the n+1 local maximums in a corresponding way. Of course, it's trivial, but all these trivial things contribute to the proof of the main theorem. Unfortunately, as I said, the whole proof has to be put into different stages. There are 3 major stages. And actually, after proving the first one, we already published the paper. So the first one, the first part says we have some initial estimates. So we had some preliminary gradient estimates. And then we have gradient log HK, first order vanishing rate, second order vanishing rate, but with additional assumptions. If you still remember what I said about main theorem, there's unconditional, the gradient estimates, the first order derivative, just 10 to 0, then Laplace is just 10 to 0. But however, this is not the case in our first publication. We proved that these estimates under certain assumptions, which is unpleasant. And then when you look at the statement closely, you will see that if this there's absolutely no relationship between delta k and the mu k. Mu k is tending to 0. Delta k is mu k is tending to infinity, and then delta k is tending to 0. So if you look at this, for example, the first order estimate, if delta k is tending to 0, very quickly, then we don't have any estimate. So this estimate will lose its meaning. So this one does not solve the case when delta k is extremely tiny. And then the same thing over here. If delta k is tending to 0 extremely fast, much faster than the speed of mu k tending to infinity, then you don't have the vanishing estimate. Okay. And also, there'll be, I think I don't have too much time to, let me talk about the main ideas in the proof. And then for n equal to 1, we have even weaker estimates. But I do want to let you know that we have uniform estimates. If delta k is tiny, and if we have a dichotomy. So when delta k is large, we have vanishing estimates. When delta k is very tiny, we can approximate the Blowup solutions by global solutions uniformly. We do have those. But that's not the main point I want to mention. I want to talk about the vanishing theorem and their applications. So I'll be using quite a few tools in the analysis, in the proof. So let me mention a few of them. The first one is that when we have a single equation, Liouville equation, globally defined, it turned out that for this equation, if you have a standard bubble and you linearize it, this linearized equation is very well understood. Suppose you have control, you have so roughly speaking, the current all functions to the linearized equation have a very explicit kernels. So all the solutions of the linearized equation can be written as a linear combination of these 3 functions. Okay, so this is done by Chen and Lin many years ago. This is one thing. I said I'll be doing a lot of local analysis on each of the n+1 local maximums. And then around each one of them, I'll be using this result, which is well known from many years ago. And then the second tool I want to use is that there'll be a lot of Pohozayev identities. What is that? If you look at the single equation, and then if you do integration by parts, you will see that there's an interior integration. B sigma is above radius sigma. On the left-hand side, you have an integration, you have interior integration. On the right-hand side, you have a boundary integration. This Pohozayev identity has been used in Blowup analysis in numerous papers. So I can't tell you how many theorems are proved by this. So what is it? If you don't know, this one is a balancing condition, which says, roughly speaking, what happens in the interior is in correspondence to what happens on the boundary. So in other words, if it is right, so there'll be a match between the interior integration and the boundary integration. And if there's something going wrong, then you can see the pathology from the balancing condition. I'm using very naive words to mention this. And then for this positive identity, so I'll be applying this QLK stand for the n+1 local maximums. So around each of the local maximum, this is derived by the positive identity. So you can see there's a gradient of the coefficient function I want to evaluate, and there's the location of the local maximum. And then there's a gradient of the phi LK, which is the harmonic function that eliminates the oscillation of Blowup solution near ULK. And there's a vanishing rate. And then this gradient of phi LK can be computed in terms of the mutual locations of the local maximums. So these n+1 local positive identities provide a wealth of information that, as you can see, let me mention a few key estimates. So each of the local maximum is a perturbation of a root of the unity. So as you can see, if I use MLK to, roughly speaking, indicate the difference between QLK and the root of the unity, and then if you throw this into the computation of the n+1 positive identities, and then you will find out that after lots of computation, you will find out that, look, the difference can be measured. It's involved with the quantity I want to estimate, multiplied by known quantities plus errors. So in other words, the difference between QLK, which is the location of local maximum, and the exact root of the unity is actually measured by the quantity I desire to estimate. And then the matrix is very specific, it's invertible matrix. And then the next, with this information, I can have even more precise estimate of certain terms in the n+1 positive identities. And then the next main observation is that I'm going to use a set of global solutions to, we know that VK, which is the scaling of the Blowup solutions, I can rescale it because the Laplacian is invariant under rotation. I can require VK to have a local maximum exact at E1, which is just 1, 0 to the 1 point at 1. This is crucial in our argument because based on that, what I want to do is I'm going to take a set of global solutions, which also has exactly 1 as the local maximum. So in other words, I require a set of global solutions that matches exactly with the Blowup solution at 1, 0 at 1 point. So they have the same value. They're both equal to a local maximum. Then by doing this, in some sense, I'm eliminating the kernel of the linear approximation. Roughly speaking, the whole story is a lot more complicated than that. And then later, what I'm going to do is that I will prove that if I take the difference between these two Blowup solutions and the global solutions, what I'm going to say that this the difference is very tiny near E1, near the origin. As I said before, I'm going to use a lot of free analysis and also Harnack inequality. So roughly speaking, that around the n+1 local maximums, I will prove that these two functions, the difference is very tiny near E1. And I'll use Harnack to pass them around the neighborhood of the n+1 local maximums. Okay, and then I'll go from there. And then, of course, I apologize for the complicated expression. So, and then for the blow-up solution, I have a Poisson fidelity. And then for the global solution, I also have a Poisson fidelity. I'm not asking you to read these two complicated Poisson fidelities in detail, but I do want to mention to you one thing. If you look at the first term on the left, for the blow-up solutions, psi any unit vector doesn't matter. The derivative of psi to the function inside, if you carry out the computation, you will see there will be a derivative on hk over here. But however, if you look at the first term of the global solution, there's no such thing because hk is the hk term is a constant. So in other words, for the Poisson fidelity for the global solution, there'll be one term about the derivative of hk, which is something I want to estimate. However, on the other hand, for the global solution, there's no such term. And then when you look at all other terms, as I said before, for the terms on the boundary, then actually the difference is also involved with the quantity I want to estimate. So in other words, and let me just explain very briefly. It says, when you subtract these two quantities, Poisson identities, when you look at the boundary terms, you will see some involvement of the first derivative of this hk. And then when you evaluate the left-hand side, when you look at the difference, you will see another relationship between calculation about the first derivative of hk. So there's an algebra between them. After carrying out the algebra, a lot of calculations, you are able to obtain the first derivatives, not only the gradient of the first gradient of the first order derivative, and also the Laplacian of the coefficient function. So I'm using like 40 pages. I'm using one sentence to describe the 40 pages of computation, roughly speaking. Okay, but at least I can, I have about 10 minutes to at least to describe the stages, the different stages of the computation. And then after knowing this, you will see that the problem, if delta k is large, then we already have the vanishing estimates. So if delta k is large, because the second quantity, mu k e to the minus mu k is tending to 0 at a certain speed. And then, but we do have a problem if delta k is very, very tiny, then we don't have the vanishing estimates. So the second stage is to talk about what happens when delta k is tiny. And then the second stage of the estimates is I need to better estimate the first order estimates. So roughly speaking, that I want to obtain a better estimate of gradient hk. That which is, for simplicity, we remove the harmonic function. Okay. And then in order to do that, I use wk to represent the difference between the blow-up solution and the global solution. And then we need to derive a very important point-wise estimate, which is this, which is also involved with the gradient hk. And also, you can treat this one as delta k squared because I only ignore mu k. It's not that important. And then we only need to consider the case when delta k is very tiny. And then another point I want to mention is that when you look at the equation, so what I want to do is I want to derive a very precise estimate of the difference of this blow-up solution and the global solution. But when I look at this equation, another key point is that when you look at the error term, the right-hand side is very tiny near E1. So I use a global solution close to E1, just 1, 0 at the point. Okay. So to make a long story short, is that this difference function is particularly easy around E1. So which means when you obtain good estimates around E1 using Fourier analysis, it will be much easier than other points. Again, long story short. And then, as I said, the analysis around E1 is just one of the n+1 local maximums. So once I know very precise information about E1, I can pass the smallness to the neighborhood of other n local maximums. That's very important. Okay. And then by Harnack inequality. And then over here, another key estimate is that I'm taking, my goal is to show that mk, which is the maximum of wk, which is the difference function, is very tiny. I want to show it is very tiny. And then, so if I use this function divided by mk, usually the analytical difficulty will be greatly magnified. And I use wk tilde, because my goal is to show that mk is very tiny. Here is the important information. So at E1, even after the normalization, I still have this wk at E1 and the gradient wk divided by 0. So this one is the stability assumption. So once you have this, even after the normalization, you can still have very nice estimate. My time is almost up, but let me just finish up. So the story says, then the next part is Ravi says, around each of the n+1 local maximums, I can choose a different global solution to make them very, very close. So around each of the local maximums, I can choose a global solution that is very close to the Blowup solution. Since my time is running out, I want to say that the pathology is, I want to obtain very precise pointwise estimates. After normalizing it, to make a long story short, is that the same Blowup solutions is very similar to different global solutions around each of the n+1 local maximums. That is not the case. So from here, you can see the correctness of the statement. So that is not happening. But why is it not happening? It takes work, but it takes a lot of work. And then the final stage, stage is once we prove the vanishing rate of the first derivative, we can improve, we do this whole thing one more time in order to obtain the precise pointwise estimates for second derivative. And then for experts among us. So what I really want to say is that the analysis around E1 is easy to obtain because the error term is easy. And then it should be the case around other Blowup points, other local maximums. But the error term around other Blowup points, they carry the Laplacian and also the gradient of the desired coefficients. So they have to tend to 0. Otherwise, how can they be the same, roughly speaking? But all of these are extremely involved. Allow me to say a few words about the impact of this theorem to other fields. Even though I only talk about the single equation, but it has a lot of applications to something called the Toda system. Toda system is a beautiful elliptic system that demonstrates a lot of connections from different fields. over the past few decades, like 5 or 6 decades, the research on Toda system has been very dynamic, and then inspirations, revolutions from different fields have pushed this research along different directions, and the new and surprising discoveries are constantly coming out. One of the major things about Toda system is that because it's a system, when you talk about the Blowup solutions, there are two major difficulties. Let me mention. The first one is that called partial Blowup. So which means, let's say you have a system of two equations. Then after scaling, you have a Blowup sequence. Then two equations became just one equation. So which means the other component converges to minus infinity. You just lose one component. This is one major difficulty. The second difficulty is that you may have multiple bubbles all coming toward one direction, toward one point. This situation is very similar to what I've been talking about non-simple Blowup. Let me just, because my time is up, so let me just mention one application about my joint work with Juncheng Wei and Mina Wu, is that when you have a sequence of Blowup solutions with both parameters tending to critical positions, it is very important to talk about parameters tending to critical positions, which I don't have time to cover. If you just assume one curvature assumption, so the importance of the Laplace vanishing theorem is that when it comes to application, you can link the analysis to the curvature. For surface, there's only one curvature, it's the Gauss curvature. You can make the assumption on the Gauss curvature, and then to say that you have an assumption on the curvature, and then suppose just one Blowup point is a fully bubbling Blowup point, then there's no bubble accumulation. So as an application, we use the same ideas for the single equation to prove this, which Rafi says, when you assume this, there's no bubble accumulation for Toda system. Everything can be so much easier. And then the theorem can be applied to many other situations, not only the Toda system, but also something called the Liouville system, and then first order equation, many things. Okay, and there are a lot of problems that need to be explored, because the quantized, most of the research is centered around non-quantized singular source. Once we know what happens to one equation, we have a great motivation to do the corresponding applications and also higher order equations. Okay, I've been talking a lot. Thank you very much. It's a lot of talk.
Okay, thank you, Professor. Okay, well, is there any question? Well, you can raise a hand if you have any question. So, yeah, well, maybe I can start with some question. And so, well, most of the work is done in the 2D, right? So
yes.
probably if you go to the higher D, and then you have a critical exponent, so then you may observe similar phenomena, and then topology and many things is more complicated. Then what kind of things do you expect there too?
Oh, this is a wonderful question, but let me just mention one difference. For example, when you consider the Yamabe equation, which is the very natural extension, Yamabe equation, in 2D, there's just one curvature, just Gauss curvature. And if you remember what I said about the single equation, you need to obtain your precise pointwise estimate until you see the Gauss curvature, which is the second order estimate. When you see the Laplacian, you'll see the Gauss curvature. Okay. But there's just one difference. When you consider the Yamabe type equations, for example, then the corresponding curvature is the wild tensor. So it's the wild tensor. So for the Blowup analysis for Yamabe equation, you need to obtain certain vanishing rate of the wild tensor, not just the wild tensor itself. You also need to obtain vanishing rate of the different derivatives of Weyl tensor, in
Yeah.
order to say the positive mass theorem can be applied, the positive mass can be defined. So as we can imagine that there are a lot of differences, but of course that's an exciting field to explore. So, of course, many things are different, but there are a lot of similarities. There are a lot of things that needs to be explored.
And also, like another question is like if you have multiple peaks, multiple blobs, then if you look at the global solution, then the center of the blow up rise on the same distance from the origin.
Yes.
So then, were there any intuition why that happens?
Oh, so the classification theorem was proved by solving a complex valued ODE. So it's an integrable system. So when you solve a certain complex valued ODE, then it comes up naturally.
I see.
Yeah. So it's very special. 2D is very special.
Well, for example, if you do have a blow point which has different distance, then it shouldn't happen, right? So somehow there should be a certain intuition for that.
Well,
instead of the computation, no?
My proof relies heavily on the structure, on the classification theorem. So because the work at the beginning seems daunting because no symmetry, but actually by exploring into the symmetry of the distribution, I was able to catch up so much information from all these. If you have a different situation, then it has to be different. But this is very, very special. Yeah. But I can also
nice.
But I can also tell you that this phenomenon appears in many different equations. So in other words, when the spherical Harnack is violated, when those bubbles all come to one point, they have to form a circle. It's very interesting. So that's why I'm asking my students to figure out the corresponding estimates for different systems, for first order equations, for many other things. Yeah.
Okay, thank you. Is there any other questions? Okay.
Yeah, Professor Ken.
Oh, hi.
Hello. Thank you for the great talk. I was wondering how far has been done in the parabolic version of your result?
I have nothing. I know nothing about it. Yeah.
Right. So, I mean, as you mentioned that all this kind of parabolic version about Yamabe problems and so on, I mean, that's obviously a very active area. And I was wondering.
I don't even know the 2D parabolic version, let alone the parabolic.
Right.
I see. Okay.
Oh, thank you for asking. I didn't know this. I didn't even realize.
Okay, thank you very much. Thank you.
Another questions?
Just, I have a short question. So again, like Ki-Ahm also asked, so the multiple peaks, they all appear at the sphere height 1, and also in higher dimensions is the case, because your picture showed only n equals 1, I think.
The picture showed n equals 3, the dimension equal to 2, okay. Yeah.
2, oh yeah, sorry, okay, n equals 2.
Yeah, yes.
Yeah.
My friend Wen Yang is here, but for first order equation, you also see such situations. For there's equation called Q curvature equation, which is very similar in many things about the very similar to Gauss curvature equation. You can also see similar phenomena, and also for system, you can see the even distribution of the local maximums. Yeah, they're very interesting. They tell you a lot of information. Yeah.
Okay, thank you. Is there any other question? Otherwise, we can say thanks again to the speaker. And then we're gonna have a tea time right after this talk. So please join the tea time and ask anything freely. Okay, thank you guys. Bye.
I just posted the invitation with the Zoom link. If anyone I missed, maybe we're sending out the coffee break information. So you find now in the chat the Zoom link for the coffee break and also the password. And please join us now just a couple of minutes after this. Yeah.
Oh, and let me copy it. Okay, hold on, let me write down.
You should have, Professor Zhang, you should have received an email, I think, with this.
Yeah, or you
Oh,
just click the link. Everything is okay.
Oh, I have the email with me. Okay. Okay.
Yeah.
You should have received an email. Yeah.
Oh, okay. Okay. I have it. Okay.
Yeah.
Okay. I just click the link. Okay.
Okay, that's great.
Okay. Bye.
Bye bye. See you soon.
Bye. Thank you, everybody.
Bye. Thank you.